2026 in Tucson. Uh, Sorry. But before we go into my work, let's do a brief summary of 3D Gaussian Splatting or 3GS. 3DGS is a foundational paper released in 2023 to solve the problem of 3D reconstruction of a scene from a few images. We obtain a structure from motion point cloud using the multi-view images of the scene, using a matcher and solver. A famous go-to for this method is ColdMap. It basically is a point cloud or a dot-ply file of points in 3D that can be triangulated given the multi-view images of the scene. We then initialize 3D Gaussians using the SFM points as centers to roughly represent the scene. Then we stretch, squeeze, or split these Gaussians over many iterations to exactly fit the renders of this 3D scene to the input images. We optimize the Gaussian attributes using backpropagation since the whole pipeline is fully differentiable. Coming to my paper, the rendering in 3GS happens using rasterization, as I have already mentioned, which is quite fast, but and also close to real time in most cases. But it is not quite fast for MR. Mixed reality applications require high refresh rates. By MR, I meant mixed reality. Mixed reality applications require high refresh rates, usually from 60 Hz to 90 Hz. We also need retinal resolution, which is usually between 4K to 8K in most VR displays. And we need two slightly shifted renders of such high resolution, one for each eye. In addition, we also have tighter compute and power budgets due to the hardware constraints, as we can't have chunky hardware chips in the headset, which increase the weight of the headsets. These issues are amplified even further when we have an untethered headset, as everything has to happen on device and you can't use an external computation core like a standard PC or Mac CPU. How can we effectively work around these issues? One idea is to take advantage of the non-uniform nature of human vision. The human vision is split into two primary regions, the foveal region and displayed as yellow in the image, and the peripheral region displayed as pink or violet in the image. Although we have a huge field of view, most of our vision is the peripheral region, with a small portion accounting for the foveal region. The foveal region is where we perceive things with highest clarity due to the abundance of rods and cones on the retina. This region of the retina called the fovea is quite small. The rest of the region of the retina is responsible for the foveal vision, which approximately is around 90% of the retina. As we go further away from the fovea in the retina, the visual acuity decreases gradually. This concept of foveal and peripheral vision is very prominent in vision science. Most of the mixed reality devices take advantage of this to some extent to reduce the compute using a technique called foveated rendering. Foveated rendering is essentially rendering concentric rings around the fovea with reduced visual acuity as we move outward. The figure on the right displays this clearly, with the clarity of region R1 being the highest and the visual clarity or acuity of region R4 being the lowest. The paper that is shown on the right is from a recently published paper called Metasapiens, a concurrent work that applies the concept of foveated rendering to 3D scenes for rendering using static concentric rings for real-time VR. Also, although this method gets significant improvements to the vanilla or uniform rendering of the scene at the same level of detail, it doesn't take into account the scene contents while rendering. Can we do better than them? Turns out we can. Our key idea is to adaptively balance perceived quality across the visual field through level of detail modulation on a patch level. At the center of our idea, we have a perceptual model, which is essentially a small MLP. The perceptual model takes as input three quantities, a target quality Q and a position vector P and a direction vector D. Both the position and the direction vector translate to an eye gaze location as displayed in the image. The perceptual model outputs a level of detail mask, which is a heat map of smooth LODs as shown on the right. The warmer regions which are towards the center, the warmer regions corresponding to the regions that have higher acuity towards the center, and the rest of the heat map, which is like colored purple, is for the less acuity regions. The green square here captures the text or a high frequency detail in the scene. As a result, it would need a higher acuity, which is shown in the heat map as it's brighter. Our perceptual model is scene-aware, gaze-contingent, and we can flexibly control the quality based on our compute constraints. How do we achieve these? As the first step, we build a level of detail structure for 3D Gaussians. In our case, this is a tree data structure where the dark green regions higher up in the tree correspond to the larger 3D Gaussians that belong to a coarser level of detail, while the finest level of detail Gaussians are stored in the leaves of the tree, marked as light green in the image. We adopt an existing method to build this LOD structure from a paper from 2024 SIGGRAPH. It's called Hierarchical 3D Gaussians. Based on the LOD, we require for a particular patch of the rendered image, we do LOD fetching by making a cut across a tree data structure as shown in the image and get 3D Gaussians on both sides of the cut that are highlighted in the image. We do bilinear interpolation to get the required Gaussian parameters for our required level of detail L. As a second step, we learn a scene-aware perceptual quality model, which is based on a quality metric, FOV video VDP. FOV video VDP stands for foveated video visual difference predictor. FOV video VDP is a perceptual quality metric for images and videos that account for how the human visual system actually processes content, particularly its non-uniform sensitivity across the visual field, as we have shown in the previous image, where we have displayed the foveal and the peripheral regions. The quality metric takes as input two patches of images, one from an LOD or level of detail of L, and the other from a reference image of an LOD of 0, along with the position vector P, direction vector D, and eccentricity E. It outputs a perceptual quality Q in terms of JOD or just objectionable difference. We need a model that takes as input the position vector P, direction vector D, and eccentricity E of the patch, and a perceptual quality Q, and outputs a level of detail for that patch. We achieve this using a lightweight MLP that's trained on these parameters to output a required level of detail, which we dub it as our perceptual model. For a required target quality Q, we split an image into patches of 64 cross 64 and run them through the perceptual model to get a smooth LOD map. Ideally, we should be running with a patch size of 1 cross 1 or 1 pixel for the best LOD heat maps. But to save on compute, we decide to go ahead with a patch size of 64 cross 64, which can be considered as a hyperparameter. As the last step, we modulate the LOD across the visual field using the predicted heat map by taking a cut across a tree to fetch the relevant Gaussians as the LOD fetching step, which is displayed here. To further reduce the load on the edge MR device, we propose moving all the heavy lifting of heat map prediction, frustum culling, and LOD fetching to the cloud, and only leave the perceptually guided rendering on the edge. We send the viewpoint with vector P and direction D tracked by the mixed reality device's eye tracker, along with the eccentricity and the target quality per patch to the cloud, and extract the Gaussians which fit our LOD heat map back to the edge as a Gaussian mask and render them on the edge using rasterization. We have our whole hierarchical Gaussian model on both the edge as well as the cloud to make this visible. To facilitate this study, we also made a data set that is photorealistic and made up of 4 synthetic indoor scenes. These are some of our results for gaze position, one of the gaze positions. The bottom left inset of each image is a corresponding LOD heat map generated by the perceptual model. And these are the results of a different gaze positions that's slightly shifted to the right, along with the corresponding LOD heat maps. On average, for both these gaze positions, we use 700,000 Gaussians per each frame. Here we show the result of the same gaze position as the last slide, but significantly lesser Gaussians of 300,000 on average for rendering each frame. As expected, the heat maps show a more frugal allocation of LODs, as we can see that the heat maps has a higher area of the violet content, which is for the lesser visual acuity. We compare our method dubbed here as perceptual, which is towards the right, with 2 other baselines of uniform and foveated at the same budget. The contents in the periphery, which are shown here, have high frequency detail, which could affect the perceptual quality, such as the screens with the text in the scene are allocated higher budget in our method compared to both the uniform and foveated baselines. This is another example showing our method adaptively assigning budget based on the scene content compared to the other baselines. Our method efficiently allocates budget and retains the perceptual quality in JODs or just objectionable difference better than the other 2 baselines of uniform and foveated. We show a plot of perceptual quality versus number of Gaussians, and our method colored in blue consistently performs better. I apologize for the unsynced videos. In addition to the objective evaluation, we conducted 2 interval force choice mixed reality user study using pairwise videos, where we show a reference video with L is equal to 0 and 2 test samples, test A and test B, and ask the user to select which test video is closer to the reference and visual quality. We conducted our user studies with 16 users. These are our results from the user study. They closely align with our objective evaluation plot that was shown earlier. In all 3 budgets that we chose, which are 300,000 Gaussians, 500,000 Gaussians, and 700,000 Gaussians, users consistently prefer our method compared to the other baselines. In summary, we develop a perceptual model to generate a LOD heat map, which we use to fetch relevant Gaussians based on the LOD from our tree hierarchy. We also propose a streamable framework where we compute intensive steps of perceptual model inference, frustum culling, and LOD fetching on the cloud side, do the rendering on the edge device by passing across a lightweight Gaussian mask from the cloud to the edge. This work is done in collaboration with Sony, I'd like to thank my co-authors, Yunxiang, Kenny, Jenna, Zenio, Maito, Kazuyuki, and Chisun. I also like to thank Yunxiang for the slides. Please check out our code on GitHub.